Okay, so we are on Module 3, and we're talking about transport protocols. There will be two videos with this module. This first one here, we're going to be looking at Transmission Control Protocol, or TCP. And of course, we've heard that term a lot throughout the semester. And it's really kind of the backbone of communication over the internet, or really any network these days. And so what we're talking about here is TCP is reliable. So the big kind of conversation we're having is why or how can TCP guarantee its delivery of every single packet? So we're talking about TCP works at the transport layer, which is layer 4. At layer 4, transport layer, it's all about creating connections from application to application. So that's from a web browser to a web browser, or an email software to an email software. So that's kind of what we're talking about. Also, application to application can also be referred to as end-to-end or point-to-point protocols. All these terms are kind of used interchangeably. And they kind of make sure that we're able to communicate with the application that is being used. Now, how does it do that? Well, we are on the transport layer. It's got the word port in it. So it uses port numbers to specify what application that particular packet belongs to. Trans with a T, if you recall the visual for the transport layer is a train. A train has different cars. Each car is called a segment. So the UDP is called segments and deals with ports. The two big protocols here are TCP and UDP. We'll address UDP in the other video, but here just a quick comparison of the two. TCP is very reliable, but it moves a little slower for that reliability, and it's typically used for unicast events when you're email browsing or sending a file, because you need to make sure you get all those packets. Whereas with UDP, it does not guarantee delivery. It tries its best, but if it loses a packet or two along the way, it really doesn't care. So that's why it's used with like Netflix when you're streaming some video, or maybe you're playing games online. Voice over IP is the phone. So with all these, we don't want a half a second delay. We want to keep moving on with whatever it is we're doing. And if a packet doesn't arrive, it's not the end of the world. All right, so let's get back to TCP. And as I mentioned, TCP is guaranteed, meaning that if it sends a packet, it makes sure that the packet is delivered and was delivered correctly. And it's delivered also in the right order, which also can be important to it. So TCP is considered a connection-oriented protocol, meaning that at first, one machine asks to talk to or connect to a different machine. Hey, excuse me, do you mind if I talk to you? And the other machine has to respond yes before that information is sent. So that's one of the ways TCP guarantees that data is connected, that data sent will be delivered. TCP is considered full duplex because, as you'll see, it's sending information back and forth, sending packets, sending acknowledgments, and all kinds of other information. So the way it creates the connection is by what we call a three-way handshake. So it does it at the startup and at the shutdown. So here is the startup. When the initiating machine says, "Excuse me, I'd like to have a conversation with you. Would that be all right?" The other machine responds back, "Yes, I am open to a conversation with you." Then the third hand comes back and says, "Gotcha, I understand you're ready for conversation." So those three steps have to take place before a connection is made, but it does ensure that both computers are ready to receive it. When it shuts down or closes a connection, the same thing happens, right? So here we have a connection. We're sending a bunch of packets. Then the sending machine says, okay, I'm done sending packets. The receiving machine says, okay, I understand you're done receiving or requesting packets, I guess, in this example. Hey, I'm done requesting packets. I understand you're done requests. Here's the rest of the data, by the way. Got it. I got the rest of the data. Now I'm done sending packets. Gotcha. Now I understand that you are now finished sending me information. And then the connection is now terminated, right? That session is over. But you have to have these communications going back and forth with TCP, whether you're starting up or shutting down. So TCP uses packet switching. So if you recall, with packet switching, a packet does not have to send or use the same route every time to get from computer 1 to computer 2. But the two computers, the two end systems, have the illusion that there's a direct connection. As far as these two end systems are concerned, there's a direct path. But we know with packet switching that it can go in any direction at all, right? So that's the nice thing about packet switching, and by the way, that's called a virtual connection. Got to get the vocabulary word in there. So when these two end machines feel or think that there's a direct connection, we call that a virtual connection because it's really not there. So here we are in the protocol stack, the networking protocol stack, right? And here we want to emphasize that TCP works at layer 4, where routers work at layer 3. So as that packet is going through the internet from router to router, from hop to hop, that router, which on layer 3 is just IP addressing, right? It only looks at the IP address. It doesn't care about TCP. It doesn't care about the port number. It doesn't care about what application is being used. It only cares at layer 3. The router only looks at the IP address and sends it on to the next hop. And that's what its job is. Now, there are some issues and some problems with TCP and the way it's set up. The way it works, sending packets, they can be lost or duplicated. They could be corrupted. They could be delayed if there's congestion, or maybe even delivered out of order. One of the computers, either the sending or receiving machine, might crash, or it might go offline, or have to be rebooted somehow. That would disrupt the flow. And or maybe the sending machine is newer and it's sending information, packets, a lot faster than the receiving computer can handle it. And so that receiving device gets overwhelmed and can crash that way. Not only the receiving device, but also switches and routers along the way can also become overwhelmed. So here's a quick visual of different causes of packet loss. So one, we've got, first of all, like the distance. This is attenuation, where maybe a cable or the distance is very long and the packet just doesn't have the strength to make it to the next hop. And then, here we've got, devices being overwhelmed, outdated or legacy devices that are just old, just not made for the current speed. There's a lot of them out there. Could be a faulty connection. So this just could be a bad, coupler or a bad link between wires that causes some packet loss, or misconfiguration or software issues. Any of those things can cause packet loss can and do, right? So TCP has a couple things set up to help prevent, to make sure that the packet gets there guaranteed. One of the things TCP does is checks for errors. So it uses, we've talked about CRCs, how that checks for errors, checksum and parity, which are kind of listed here also. They're all kind of the same thing. They all do kind of the same thing in a little bit different way, but they're all double checking to make sure that all the ones and zeros that were sent arrive, and those ones and zeros are in the exact same order as when they were sent. So that's error detection. Besides error detection, TCP has techniques that address these other issues. Sequencing, things arriving out of order, packet loss, duplicate packets, flow control, like how fast you send something, and kind of bursts of packet causing congestion. We're going to be talking about these issues in the next few slides. And we'll start off with sequencing. So how does a receiving computer know if a packet was sent out of order or if there's a duplicate packet? Well, it's because every packet has a number associated with it. And the sequencing number will tell the receiving computer, okay, hey, this is the next one in line. And if something shows up out of order, it'll store it in its memory or its buffer until the other packets catch up, and then it'll pull the early packet out of the buffer, out of memory, and send it up through the line. That's the same thing with duplicate packets. If it receives a packet that has the same sequence number, it knows it's a duplicate, and it'll just discard the extra packet. So the sequencing number helps put it in order, right? 1, 2, 3, 4, 5, and make sure that duplicates do not get in the mix. Another way TCP handles packet loss is with retransmissions. So if a sending machine does not get an acknowledgement that that packet was received, then it will retransmit or send a copy of that packet to make sure it gets there. How long does it wait, though? Well, it waits a certain amount of time. When it sends a packet, it starts a timer. And if that timer runs out, then it's going to send that packet again, a copy of that packet, because it is going to assume that the packet was lost, right? So again, if the timer expires before acknowledgement arrives, it sends another copy, right? And that's called retransmission. So if it waits really long, right, then that could lead to, some other issues, right? So in this example on the slide, a computer sends 10 packets. Only three packets don't arrive right away. So it waits, and then it's going to send those 3 packets again from a second conversation. Now, this is all of a sudden now, both packets, the first packets and the second package sent arrived. So now we've got duplicates. So that's one way duplicates can happen. And that's where that sequencing numbering comes in to make sure that the extra packets are not used. We're still talking about duplicate packets here. Not only can the information be duplicated, but also the control packets. When we're setting up, establishing, and ending a connection, you can maybe duplicate those also. So like if he sends a message here saying, hey, I'm finished, and he does not get an acknowledgement back, he might send another packet saying, did you get me? I said I'm finished. Let me know if you heard me, right? So you can get duplicate packets in the 3-way handshake, opening and closing also. Now here's another little kind of twist in here where that sequencing or unique ID is important. If this sends a message saying, hey, I'm finished, doesn't get acknowledgement, sends another one, the connection's closed, then they reestablish a new connection for a different file to send. Okay, now that original finished packet arrives from the last session. Well, that could be confusing for the receiving computer. Oh, wait a minute. Did you want to finish this one, or was that for the last one? Well, each session has a unique ID with it. So if that duplicate packet arrives late while a new session was established, the receiving computer will disregard it because it says, "Oh, wait a minute, that ID was from the last conversation we had, so I don't need to listen to that." All right, let's move on to flow control. How fast should we send packets? And what do we do if the receiving computer or router is getting overwhelmed, right? So maybe one computer sends packets a lot faster than the other computer can receive it. Well, we got two techniques we're talking about here. The first one's stop and go, and this is just where you send one packet and you wait for an acknowledgement. Then you send the next packet and you wait for acknowledgement. So you're sending one packet at a time and waiting for the acknowledgement on each packet. Very secure, but also very slow. That's low throughput, right? We're not getting a lot of information through very fast. Option B, it's what we call a sliding window. And what works with a sliding window is basically kind of a buffer space. So we're sending information in chunks. So I'm going to send 4 packets at a time. And I'm going to wait to get 4 acknowledgments. Then I'll send the next 4 packets. And by chunking that information, it increases the throughput or the speed, right? But those extra packets have to be stored in some type of memory or buffer space until the operating system can process it. So here's an example here of the buffer I was talking about. So maybe you send 4 or 8 packets. The buffer or memory stores it. The operating system processes those packets as fast as it can and sends it up to the ultimate application, which again is like email, web browser, whatever it is. This graph down here shows how the winding or sliding window works. So here's the packets we want to send. We're sending 4 packets at a time. Maybe we only got the acknowledgement back for the first 2, in which case the next 4 packets are sent. So 2 of these packets are retransmissions. And again, we wait for the acknowledgement packet, and then we send the next ones, and we're sending a window or a chunk of 4 packets at a time. And that kind of helps control the speed of which the receiving computer or device gets the packets. So here's another kind of situation. What if, how do switches and routers get overwhelmed? So let's just pretend here for a minute that all these computers and devices can handle data up to 1 gig per second, right? 1 gigabit per second. And so, and by the way, side note, 1 gig a bit, right? If it's a small b, we're saying 1 gigabit per second. If it's a capital B, that means it's 1 gigabyte per second. So you always kind of have to pay attention if that's capital or lowercase, because that does make a big difference. So in our example here, both computer A and computer B is sending information to the switch at 1 gigabit per second. So switch 1 is receiving information at 2 gigabits per second. 1 gigabit from A, 1 gigabit from B. But switch 1 can only send 1 gigabit of information. So you can see how it can very easily be overwhelmed in this situation. And as the switch 1 struggles to forward on all those packets, and it takes its time to do it, maybe computer A and or computer B has to retransmit packets because it thinks it's lost. Well, that will just add to the convention or the congestion. So it's kind of a self-fulfilling prophecy sometimes. Guys, I'm not going to take time in this video here to show you this video on Lucy and Ethel, the chocolate factory, but you do want to Google that and watch this.
This February at Renewal by Andersen, replace your windows, your patio doors, or...
All right, girls,
just want to show you kind of what it looks like. Is the volume off here. Watch this. It's only 3 minutes long, but it's a good example of what it looks like to be overwhelmed, a router to be overwhelmed. So take a look at that. Maybe we'll show it in class. I don't know. Okay, let's move on. So how does TCP communicate that there's a congestion issue out there on the internet, either the switch or the router or the receiving computer? Well, they have a couple of different ways to do that. First of all, if the router is having issues, then it might put an extra bit in the header telling the receiving computer that there's congestion. Say, hey, I know packets are coming your way, but I'm really busy, so it's going to be slow. Then what might happen is it uses an algorithm to say, okay, based on what I was just told, instead of expecting this in 10 milliseconds, maybe it's going to take 30 milliseconds. So it can adjust its estimate. Also, that receiving computer will send information back in the acknowledgement to the original sender saying, hey, just so you know, it's really busy out there. Expect things to take longer. So again, there's that communication between devices. Sort of like here at school, sometimes in the morning, there might be a train at the bottom of the hill on North Bend, or maybe there's an accident on the way. And all of a sudden, it's getting close to 8 o'clock and people are starting to come in late. And so if a lot of people come in late, they know that there's congestion out there, maybe an accident on a train. And if it is really bad, right, the administration will get on the announcements and say, hey, there's an accident out there. Students will be coming late. Please let them into class. So now teachers know students will be coming in late, and it's approved because it's not their fault. There's an accident or congestion out there on the way into work or way into school. So that's another way they handle congestion. So once information starts being sent and gets overwhelmed and packets start being lost, how does it respond? Well, it responds, the sending machine responds by reducing the rate at which the packets are being sent. So in this example here in the graph, right, it's sending packets and then it's going well, so it sends more and more and more and more until it gets to a point where their packets are being lost. And then it'll automatically drop back down to a lower or a slower rate and then start sending those packets again. Once it reaches to a critical congestion point, it'll stop or slow down at least, reduce the rate, and kind of build back up again. So you kind of got this constant building and slowing until it finds that right level of the right level of sending throughput. I will mention this, guys. Most of the congestion is caused by bursts of packets. Very rarely is it hardware failure. It's possible that a router breaks or goes down, but and it does happen, but it's not typical. Usually, if there's hardware or packet loss or delay, it's from congestion. Okay, so how does TCP handle packet loss? Well, they got a lot of different or a variety of schemes or a lot of different techniques to achieve that reliability or that guarantee that the packet is delivered. One is retransmission. So if it takes too long to arrive, then it will send it again. Another one is the acknowledgement. So for every packet it sends, it waits to get an acknowledgement back from the receiving computer saying, yes, I got it. And then another technique is a timer, in which case when it sends a packet, right, how does it know when to retransmit? Well, it knows it waits for a while. And if it doesn't receive the acknowledgement back, then it will do a retransmission. So think of this timer as sort of like a time to live, right? Counting the hops. Instead of counting the hops, it just counts how much time is sent. So here, it sends a packet, gets the acknowledgement, sends the packet, gets the acknowledgement, sends another packet, but this one gets lost. It doesn't get an acknowledgement, so it resends that packet 3 again and then moves on. So that's kind of how that works. How long does it wait before it retransmits a packet that didn't arrive or you didn't get an acknowledgement from? Well, that depends on where it's coming from. So if we're in a LAN and it's going from one computer to the next inside a internal network, say here at school, then it should arrive within a few milliseconds. If you're going across the country or across the world, you're using satellite connections or whatnot, it could take hundreds of milliseconds. Remember, a millisecond is 1/1000th of a second. So that's pretty quick, right? Communication. Another kind of cause of congestion is a burst of packets. So maybe a computer is on a network and the network has a certain level of capacity and it's doing just fine. But as we kind of talked about it a few minutes ago, maybe a computer or two computers all of a sudden are downloading or sending a huge file. And you just don't send a couple packets, right? You're sending thousands of packets at a time. And so now all of a sudden there's a burst of communication, a burst of activity in that network that sends it past its capacity level and into the overflow or overwhelmed state, in which case these packets are lost. The packet rate, as we talked about, would slow down and they would start sending it again and start building it back up again. So bursts of packets can also cause congestion. But TCP can adapt, and that's one of the great things about transmission control protocol, right? So as we are kind of doing the slow start, where it sends one packet and then 2 and then 4, then 8, then 16, and then it keeps sending more and more, but all of a sudden it realizes, hey, I'm losing packets here. I'm very congested. TCP will adapt and slow down the transmission. 1 packet, 2 packets, 4 packets, 8, 16, right? And then all of a sudden it'll actually 10 packets. And then once it starts to overwhelm, it'll slow down again and kind of build back up. So it throttles the number of packets it sends up or down, depending on the feedback it's getting on how congested the network is. So it's very adaptive. How does it know or how long to wait, right? How does it figure out what the congestion is out there? Well, it takes the information it receives from routers and the receiving computers and estimates how long it should take the round trip. Then it kind of uses an algorithm to come up with that number. Is it 10 milliseconds? Is it 500 milliseconds, right? Somewhere in there, it comes up with a determination. This image right here is of Wireshark. And you can see the black packets, and black typically means there's an issue. A lot of those are retransmissions saying, hey, this TCP packet didn't arrive, I'm sending it again. So it's a retransmission. You also have some duplicate acknowledgement packets in here. And then you have some regular acknowledgement packets and regular TCP packets that arrived on time. So again, you can kind of analyze what the packets are and what's going on in your network using Wireshark. So now we're on to talking about the buffer and the sliding window. So when two devices make a connection, right, they create buffers to store the packets until the operating system is able to process them and send them on up to the final application. The window size, and again, this little image here is from Wireshark, and one of the pieces of information tells you the window size. That's another name for the buffer. Okay, my window size is this much. You can send me this many packets before I start losing them, right? And so you can kind of track how big or how full the buffer is by looking at the window size. And so it works like this. Again, we're still talking about the different window sizes. The receiving computer sends out a message saying, hey, I can handle 25. Let me just zoom in here, make it a little bigger for you. I can handle 2,500 octets. So then the receiving says, got it. So he sends 1,000, gets the acknowledgement, sends another 1,000, gets the acknowledgement, sends another 500, gets the acknowledgement. Notice then, after that last one, the window size is 0. So it stops sending until the receiving computer sends the acknowledgement saying, okay, I am now ready to receive some more, up to 2,000 octets. So the sending machine will send another 1,000 and then another 1,000. The window is now down to 0. It stops, waits for the acknowledgement to say, okay, my buffer is now open again. You can send another 1,000 packets. So that's kind of the way it works. Okay. This slide talks about the three-way handshake, which we've already kind of covered in the earlier slide. When a computer creates a connection, either establishing or terminating, right, it uses a three-way handshake. So one computer says, hey, I'd like to talk with you. The other computer responds, I understand you'd like to talk with me, and I'm okay with that. Then the third acknowledgement is, thank you for letting me talk with you. And after those three interactions, then a connection is established between the two computers, right? Until these three things happen, nothing will be exchanged. No packets will be exchanged. Not only is that three-way handshake used to create a connection, but it's also used to end the connection. So here's the what we just went over, establishing a connection. This one is ending it. So the client says, hey, I'm done sending you information. Fine, I'm done receiving information. Got it. You're now finished, and we are now done. So this session is closed after that three-way handshake. But both computers have to agree to close it before the connection is terminated, right? So SYN stands for synchronizing, right? And then FIN is the finishing. It tells you to finish. That's what that stands for. So what happens if a connection is made, a connection is terminated, and then a new connection is made between those same devices? It can be confusing depending on how and why a connection was terminated. Well, this slide says for every new connection, TCP uses a new random number for that connection, right? So, this is connection number, 58. And then when that connection ends and it creates a new one, new random number could be 232. And so if the receiving computer gets a packet from the original connection, it knows that it doesn't apply to this session. Hopefully I said that correctly. If you're not sure on what I just said, ask me in class and I'll go over it again. So again, we're talking about congestion again and how retransmission how retransmission can actually worsen congestion. Because if a machine's being overwhelmed, packets aren't getting through, no knowledge is being sent, the receiving or the sending computer sends them again. And if it sends it again, that adds to the congestion. So packet lost can be caused by network congestion, which we've talked about, overloading devices, which we've talked about, faulty hardware, which is rare but can happen, right? And some of these other issues can cause it, right? But in any case, anytime there's congestion, the sending machine will reduce the rate of transmission to slow or reduce the amount of congestion out there. Also, it can be based on the buffer size. So again, having a full buffer size will also reduce the rate of transmission, hopefully reducing congestion. By temporarily reducing the window size, right, we are reducing the rate. So instead of sending, say, 4 packets at a time, maybe we're only going to send 2 packets at a time and reducing the window size that way. To get to the right window size, like how many packets can you do, we use that slow start. So we start by sending a single message and then kind of go from there. So here's that example, right? This is a slow start. It sends 1, waits for the acknowledgement, and then it'll send 2, waits for the acknowledgement for those, sends 4, waits for the acknowledgement, sends 8, and keeps building up until it's congested, and then it starts back down again, right? So once half of the original size is reached, right, so the buffer is starting to get full, then TCP will start slowing the rate of increases. And or if it gets full, then it'll stop or reduce or start over again, right? So that's all kind of a slow start. By backing off quickly, the hope is it avoids congestion. So this is what the header looks like for a TCP packet. Notice that we do not have IP addressing or MAC addressing here because TCP doesn't care what the IP address is and doesn't care what the MAC address is. It cares about what the port number is. What application is this going to be used for, right? And this header is used whether we're carrying data or acknowledgement or the three-way handshake. It doesn't matter what type of packet is being sent. We use the same header, right, on this. So again, this is just a breakdown of the header, and I'm emphasizing the source port. So if it's an email, it'll be port 25. If it's a web page, it'll be port 80. Now it knows what application to forward to this to once it receives it on in the receiving computer, right? We've gone over these other aspects of the header. So if you're not sure what they are, read through them, and I'll answer any questions you want. But you should be familiar, at least we've talked about all of these different segments in the past. So we've been talking about TCP, that guarantees delivery, and it has all of this information in the header, including the sequence number, the acknowledgement number, the window size, all that other stuff, right? The next video, or the sister protocol to TCP, is UDP. And notice that this header is a lot smaller. We have no sequencing number, we have no window size, so it moves a lot faster because there's lower overhead. The downside to UDP is it's not guaranteed. So a lot of these packets get lost and they're never recovered. But that's okay in certain situations, which we'll talk about in the other video. All right, so just went through a lot of information. Look through these topics. You should be familiar with them for the test. And as always, if you have any questions, hit me up in class, and I'm happy to review it with you. Good luck.